Okay, good morning, guys. Our topic for today is all about the different devices used to measure flow of fluids in a piping system. So, our topic is measurement. Okay, measurement of flow of fluids. Okay, so the very first, there are a lot of measuring devices that is being used and included and embedded in a piping system. Now, it is important to be able to measure and control the amount of material entering and leaving a chemical or other processing plants. Now, since many of the materials are in the form of fluids, they are flowing in pipes or conduits. Many different types of devices are used to measure the flow of fluids. The most simple are those that measure directly the volume of flow fluids such as ordinary gas and water meters and positive displacement pumps. Current meters make use of an element such as propeller or cups on a rotating arm which rotates at a speed determined by the velocity of the fluid passing through it. Now, a very widely used for fluid metering devices or fluid metering are number one, the pitot tube, the venturi meter, the orifice meter, and the open channel weirs. So, we'll be discussing all of them today. Okay, the very first one is the pitot tube. Okay, pitot tube is used to measure the local velocity at a given point in the flow stream and not the average velocity in the pipe or conduit. Okay, take a look at this particular figure in here. So this is the flow, okay, and these are the points, point 1 and point 2, and this is your pitot tube, okay. Um, this particular tube is what we call the impact tube. It has its opening normal to the direction of flow, and the static tube has its opening parallel to the direction of flow. So, meron siyang tinatawag na static tube. Now, the fluid flows into the opening at point 2, then the pressure builds up, then remains stationary at this particular point. And this is what we call the stagnation point. So, nagkakaroon ng build up ng pressure. Yun yung stagnation point. Now, the difference in the stagnation point pressure at this point 2 and the static pressure measured by the static tube represents the pressure rise associated with the deceleration of the fluid. So again, for us to be able to calculate for the delta P, you must have the static pressure measured by the static tube. Okay? So, yung una, yung stagnation pressure, then the other one is the static pressure. Okay? Now, for us to be able to calculate or to know the equation for this particular device, okay, again, puntahan uli muna natin si Bernoulli's equation. Remember, our flow is similar to this one. Okay, you have a pipe, then you have a pitot tube. This is your pitot tube, no? The flow is at this particular direction. So, ganyan. Then you have here your point 1 and your point 2. Okay, so yung point 2 yung stagnation point or the stagnation pressure at point 2. Tapos, kailangan malaman natin yung static pressure. Okay, so if this is the direction, Ano nga ba equation natin for Bernoulli? We have delta P over density plus delta B squared all over 2 GC plus delta CG over G sub C plus the summation of all the friction losses plus the shaft work is equivalent to 0. Now, since the system is too small, then the friction losses is equated to 0. And walang pipe dun sa system. So, shaft torque is equivalent to 0. And wala ring elevation. So, this will become 0 also. Leaving us with the equation, we have delta P over density plus delta B squared all over 2 for SI is equivalent to 0. Now, if we manipulate this one, this will become P sub 1 squared over 2 P sub 2 squared over 2 okay, plus delta P over density. Now, if we this is equivalent to 0. If we transpose this particular term into the other side, okay, sa kabila, then we're gonna have V sub 2 squared over 2 minus V sub 1 squared over 2 is equivalent to negative delta P over density. Then, ang kailangan kasi natin dito is the initial velocity. Assuming that your V sub 2 squared is equivalent to 0, or if we set V sub 2 to 0, kasi hindi naman natin kailangan na yun. Yung V sub 1 lang kailangan natin. Then, your V sub 1 squared is equivalent to 2 delta P over density. Or, your V sub 1 is equivalent to the square root of 2 delta P over density. So, this is your equation for pitot tube. If we want to know the velocity of the flow dito. Yan. Diyan. Now, since nasa gitna yan, most probably, ang pwede nating makuha dyan is the maximum velocity. Remember, in the flow inside the pipe, ang pinakamataas na velocity is yung nasa gitna. Okay. Now, to further simplify this one, your V sub 1 then is equivalent to C sub P square root of 2 delta P over density. This is your equation for pitot tube. Okay, wherein your C sub P is the pitot tube coefficient. Okay, this is your coefficient. Now, the values of the coefficient is, depende yan, no? Most of the time, it's 0.98 hanggang sa around 1.0. Depende dun sa material or dun sa device na nakalagay. Okay? Okay, so basically, since yan ay manometer, then remember our equation, delta H, or rather delta P, is equivalent to delta H, quantity, density A minus density times G. Remember this particular equation before? Okay. So, for us to easily understand this particular equation, let us solve this particular problem. Now, a pitot tube, which is similar to the one that we have kanina, no, the figure, is used to measure the airflow in a circular duct. Okay. So, we have a circular duct. So, this is the flow. So, ito yung pitot tube. then this is the manometer. So yan siya, no? Then the diameter of the duct is equivalent to 600 millimeter. The flowing air temperature is around 65.6. So the temperature of the air that is flowing inside a circular duct is equivalent to 65.6 degrees Celsius. The pitot tube is placed at the center of the duct, and the reading delta H on the manometer is equivalent to 10.7 millimeter mercury. A static pressure measurement obtained at the pitot tube position is 205 millimeter of water. Okay, so meron tayong 205 millimeter of water. So yung pressure yung pressure na static is equivalent to 205 millimeter of water, but it's above the atmospheric. Okay, so which means that this is stress gauge, so we're gonna have to add 1 atmosphere into it. Okay, and the pitot tube coefficient C sub B is equivalent to 0.98. So we are required to calculate for the velocity at the center, which means B max, and the V average. Then of course, letter B, we're being asked to calculate for the volumetric flow rate of the air. Okay, so solution. Okay, solution. Remember the formula. Okay, the velocity is equivalent to C sub P square root of 2 delta P over density. So, kailangan natin makuha yung delta P over density, or rather yung delta P. Now, sabi dun kanina, delta P is equivalent to the difference between the stagnation pressure at saka yung static pressure. Okay? Now, so, para makuha natin yun, before we proceed with that calculation, kunin muna natin yung mga properties nung air flowing inside the pipe. So, properties of air. Okay, we're given the temperature, which is equivalent to 65.6 degrees Celsius. Okay, using this temperature, we can have the viscosity. Okay, we may use the Paris Chemical Engineering Handbook or the appendix at yung kay Gian Coplis or yung kay McCabe. So, viscosity is equivalent to 2.03 times 10 to the negative 5 Pascal second. While its density at this particular temperature is equivalent to 1.043 kilograms per cubic meter. Now, to calculate for the absolute static pressure, okay, kasi kailangan natin yung difference ng dalawa, remember? Okay, yung stagnation pressure at saka yung static pressure. So, calculate muna natin yung static pressure. Okay, delta P static pressure. And this can be calculated utilizing, of course, yung delta H static. We're given na yung P static 205 millimeter mercury. So that's your delta H for the static, multiplied by the density of water minus the density of air, multiplied by the value of your G. Okay, this is then equivalent to, your delta H is equivalent to 0.205. Okay, this is in meters, multiplied by the density of water, that's around 1,000 kilograms per cubic meter, minus 1.043 kilograms per cubic meter, multiplied by 9.81 meters per second squared. The answer will be equivalent to 2008 Pascal. Okay, then the absolute static pressure then, kasi above daw siya, no? Above the atmospheric, will be equivalent to, so your P1, absolute static pressure, is equivalent to yung 1 atmosphere, 1.01325 times 10 to the 5th Pascal plus 0.02008, okay, times 10 to the 5th Pascal. Para-pareho sila. Then your absolute static pressure is equivalent to 1.0333 times 10 to the 5th Pascal. Okay? Now, we can utilize this particular pressure for us to be able to obtain the correct air density, okay, that is flowing inside the pipe. The correct air density is equivalent to, of course, the atmospheric pressure, rather P sub 1 all over the atmospheric pressure. P sub 1 all over the atmospheric pressure multiplied by the density that we got, the air. This is then equivalent to 1.0333 times 10 to the 5th Pascal divided by 1.01325 times 10 to the 5th Pascal multiplied by 1.043. Then the corrected density of the air is then equivalent to 1.063 kilograms per cubic meter. This is then the corrected density of the air. Now, to calculate for the delta P for the pitot tube, okay, so the delta P for the pitot tube, this is then equivalent to the delta H dun sa manometer multiplied by density of A minus density of B multiplied by the value of G. This is then equivalent to 10.7. This is in millimeter. Divide this by 1,000 multiplied by 1,000 minus the density of the air, which is yung corrected na 1.063 kilograms per cubic meter. Multiply this with 9.81 meters per second squared. The answer is then equivalent to 104.8 Pascal. So this is your delta P for the pitot tube already. Now, for us to be able to calculate the maximum velocity then, using the formula C sub P, square root of 2 times delta P all over density. And given from the problem that your C sub P is equivalent to 0.98 multiplied by the square root of 2 times 104.8 Pascal divided by the corrected density of air, which is 1.063. The maximum velocity then is equivalent to 13.76 meters per second. This is the maximum velocity. Now, if we want to obtain the average velocity, we can utilize a figure from the Gentkoplis, book of Gentkoplis, that shows the relationship between it's a graph, the relationship between the Reynolds number and the average velocity and the maximum velocity. Okay? So first, we calculate for the Reynolds number using the maximum velocity. So Reynolds number, NRE, is equivalent to the Vmax density all over the viscosity. This is then equivalent to the diameter, which is 0.6 multiplied to 13.76 maximum velocity times the density, the corrected 1.063 kilograms per cubic meter, divided by the viscosity that we got, which is 2.03 times 10 to the negative 5 Pascal second. The answer will be equivalent to 4.323 times 10 to the fifth. Okay? Using this particular value, then i-project natin using yung figure 2.10, figure 2.10-2 Gentkoplis. Okay, we can have the ratio of B average divided by B max Okay, B average over B max is equivalent to 0.85. Now, we have the B max. Tapos, meron kang value ng ratio of B average all over B max. Then, we can calculate for the B average. This is then equivalent to 11.7 meters per second. So, this is your average velocity. Okay. The next requirement is, of course, the calculation of the flow rate. So, sa flow rate, first, kailangan natin ng area at saka ng velocity. We already have the average velocity. Kailangan na lang natin is yung area. Remember, area is equivalent to pi d squared all over 4. So, you have pi, quantity 0.6 meters squared all over 4 is equivalent to 0.2827 meters squared. So, you have your area, tapos meron kang velocity, average, then we can calculate for the volumetric flow rate. So, volumetric flow rate then is equivalent to 0.2827 meters squared multiplied by 11.7 meter per second. So, the answer is equivalent to 3.308 cubic meter per second. So this is your volumetric flow rate obtained using the pitot tube.